Hi everyone, welcome to the classes on fluid machinery. In today's class, we'll be discussing the second topic in the sixth module, that is the axial flow compressor. So, in today's class, we'll discuss a general layout and working of an axial flow compressor. Also, we'll discuss how the velocity diagram will be for that axial flow compressor, and we will discuss two problems in connection with the axial flow compressor. So, here is a sketch of our axial flow compressor. It consists of a casing and it have two sets of blades or vanes, that is called S is marked as stator blades and R is marked as rotor blades or rotor vanes. The stator blades are fixed and it is fixed to the casing, and the rotor blades are moving, which is fixed to the rotating drum. And in the figure you can see that the area of flow is decreasing from inlet to exit as the diameter of the drum is increasing. In some other case, the casing diameter is reduced. In this figure, the rotating drum diameter is increased. That's why we can reduce the airflow area from inlet to exit. When power is given to the compressor, the rotating drum rotates and it creates a suction in the compressor. Due to the suction, air enters through the compressor inlet passage and passes through the rotor and stator blades. Okay. As the air flows from one set of stator to rotor, another it gets compressed. The air is also compressed between the casing and the blades. The pressure of the air is further increased due to the gradual decrease of area from inlet to outlet. Finally, the high pressure air is delivered to the receiver. Now we'll go through the velocity diagram for this axial flow compressor. And it is little bit different from our normal centrifugal compressor or centrifugal pump like that. So we have to study this velocity diagram for solving the problem in connection with the axial flow compressor. Small variations are there. We will be marking alpha 1 and beta 1 instead of alpha and theta, and we will be marking alpha 2 and beta 2 instead of beta and phi. Okay, we have three velocity triangle. First is the inlet velocity triangle, second one is the outlet velocity triangle, and third one is the velocity triangle for the stator blades. The first two triangle is for the rotating blade or rotor blade, and the third one is for the stator blades. The fluid will be leaving with a velocity c3 at an angle alpha 3 from the stator blades, and you will be marking alpha 1 and beta 1 with the c1 and cr1, and we will be marking cb1. It is the blade velocity. Initially we will be marking as u for the previous case. Now it is marked as cbl, and instead of v1 we will be marking c1, instead of vr1 we will be marking cr1, and instead of vw1 we will be marking cw1. Okay, and the remaining term instead of u1 minus cw1 they have marked as crw1. Okay, and the outlet velocity triangle will have c2, cr2, cw2, and the remaining term crw2. Okay, and from the velocity triangle we can write tan alpha 1 plus tan beta 1. So this is a tan angle. Tan is equal to opposite side by adjacent side, opposite side by cw1 and adjacent side by cf1. Tan beta 1 opposite side equal to crw1, adjacent side cf. Again, if we are adding this, cr1 divided by cf plus cw1 divided by cf, as the denominator is common, we can write cw1 plus cr1, which is equal to cbl. So we can write cbl by cf is equal to tan alpha 1 plus tan beta 1. Similarly, for the bottom velocity triangle, outer velocity triangle, cbl, that is the blade velocity, divided by cf is equal to tan beta 2 plus tan alpha 2. So these two relations are derived from the triangle. Okay. And the work done, normally we will be calculating the work done in terms of vw1 minus vw2 into u. The same is repeated here. we will be multiplying the velocity, blade velocity CBL with the world velocity, difference of world velocity CW2 minus CW1. Okay. And as we are dealing with air, we can write the same work done equation with the help of temperature change. So we will be writing Cp delta T for the work done. So if we multiplying with mass, we will be this is the work done per kilogram of air. If you want to get the total work done, we have to multiply with the mass of air we are dealing. And we can also represent the work done equation in terms of CF. Suppose in our question only the value of CF is given, we have to convert the CW1 values into CF, as the CW is a part of triangles. Tan alpha is equal to CW by CF, or CW is equal to CF tan alpha. So we will be replacing CW with the CF tan alpha 2 or CF tan alpha 1, and we will get the value of work done in terms of CF. So okay, again we can replace with the tan beta 2 and tan beta 1 and tan beta 2. Okay, and the next thing we have to study the pressure rise. Initially the pressure is P1 and initial velocity is C1. Due to this velocity, the P1 is called the static pressure, and due to the inlet velocity the pressure is increased to P01, that is called the total pressure. And the pressure is increased to a term P2 with a outlet velocity C2 square by, so the total pressure rise is equal to P02, which is given by P2 plus velocity component. Okay, so we have to calculate the total pressure rise by using P2 minus P1 is equal to C1 square minus C2 square. That is gives the total pressure rise in the equation. And the next thing we have to study the degrees of reaction. RD is given by pressure rise in the rotor blades divided by total pressure rise in the stage. The pressure rise in the rotor blade is given by the difference between the relative velocities. And the total pressure rise is equal to work done, or the total pressure rise is equal to work done per kilogram of CBL into CW2 minus CW1, or Cp delta T. We can use both equations. That is the total pressure rise or total work done in the stage. And the pressure rise in the rotor blade means it is only the difference between the relative velocity. Okay. And for the normally in many questions they have given the degrees of reaction as 0.5. That means alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. There are derivations for this. Normally they won't ask this derivation, so we'll be studying with the minimum topic. Okay, so here is our first question. The following data related to axial flow compressors with blade velocity CBL is equal to 240 meter per second and CF velocity of flow is equal to 190 meter per second. Alpha 1 is equal to 45 degree. Alpha rho is equal to 1 kilogram per meter cube. And they have marked alpha. Actually it is alpha 1 is given, it will be alpha 2. Okay, alpha 2 is equal to 14 degree. Rho is equal to 1 kilogram per meter cube. Pressure rise, we have to calculate the pressure rise, that is P2 minus P1 we have to calculate. So we have to calculate the pressure rise, and the next thing we have to calculate the work done per kilogram of air. So this is a total pressure rise equation. P1 by rho plus C1 square by 2 equal to P2 by rho plus C2 square by 2. Okay, so we have to calculate the difference between P2 and P1. That is the first thing we have to calculate. So P2 and P1, P2 minus P1 is equal to, so we can write C1 square plus C1 square minus C2 square by 2 into rho will gives the value of P2 minus P1. And the work done per kilogram of air, we got a two formula, either in terms of blade velocity or in terms of pressure we can calculate, or in terms of temperature we can calculate it. So here is the given data. Blade velocity CB is equal to 40 meter per second and CF is equal to 190 meter per second. Alpha 1 is equal to 45 degree, alpha 2 is equal to 14 degree, and rho is equal to 1 kilogram per meter cube. So first we will calculate the pressure rise, which is P2 minus P1, that is given by rho into minus of C1 square minus C2 square. Okay, so as we are taking that side, and C1 square from the triangle C1 square can be written as it's a right angle triangle. C1 square can be written as Cf square plus Cw1 square. Okay, and C2 square, again C2 square can be written as Cf square plus Cw2 square. So as Cf square are both same, Cf1 square and Cf2 square are same, they got cancelled. The remaining will be Cw1 square minus Cw2 square. So we will get the value of total pressure rise as Cw1 square plus Cw2 square. Cw1 can be written as in terms of Cf tan alpha. So Cf is taken outside. So we can write Cf into tan alpha 1, that is for Cw1. So we are writing Cw1 square. So Cf square tan square alpha 1 and a Cf square tan square alpha 2. Cf square is taken outside. So we will be right 1 rho by 2 into Cf square square tan square alpha 1 minus tan square alpha 2. This is the total equation for the pressure rise. And we will be substituting the value 1 by 2 into Cf. The value of Cf is given 190 divided by rho is given as 1 kilogram per meter cube, and alpha 1 and alpha 2 is given. So we will get the pressure rise as 0.169 bar. Okay, this is the first time we have calculated. The second time we had to calculate the work done, as the temperatures are not given and we got the value of blade velocity. So we will be using the equation for blade velocity for work done, CBL into Cf tan alpha 1 minus tan alpha 2. As Cw1 is not given, so we already got the value of Cf. We will be substituting. Normally the work done equation is equal to blade velocity into Cw2 minus Cw1, and we will be replacing with the Cf and tan alpha 1 and tan alpha 2. So we will got the value of work done is equal to 34.23 kilowatt. Okay. So here is our second question from the axial flow compressor. So an axial flow compressor having 8 stages. So initially we have seen in our figure a set of rotor and stator blades. So one set of rotor and stator blade will give you one stage. So in this compressor such 8 sets are there, so we will be compressing in 8 stages. So if we are writing the equation for work done in terms of blades, we have to multiply with the number of stages, because we are writing the equation for one set of stator and rotor blades. So and if we are writing the equation in terms of temperature, we don't need to multiply with the stages. So we are writing the temperature at the inlet and outlet of the compressor. So we will be dealing with the total compression inside the compressor. Okay. So here is an axial flow compressor having 8 stages with a 50% reaction. Design the compressor air in the pressure ratio 4:1. Pressure ratio is given, P1 and P2 will be in the ratio of 4:1. The air enters the compressor at 20 degrees Celsius. T1 is given as 20 degrees Celsius and it flows through it with a constant speed. Velocity of flow is given 90 meter per second. The rotating blades are compressor rotate with a mean speed of 180 meter. Blade velocity is given as 180 meter per second. Isentropic efficiency of the compressor can be taken as 82%.